Welcome to Stree Info for You channel. In this channel, we are going to see the multiple choice questions for discrete time signal processing or digital signal processing, IAR filters. So, IAR filters, in this topic, we are going to see IAR filters basics and impulse invariance method. Some 30 questions we are going to see now. So, the first question is IAR filters are designed by considering all the dash. So we know IAR filters are infinite impulse response filters. As the name indicates, it is having infinite samples. So IAR filters are designed by considering all the infinite samples of the impulse response. So the answer for this option B. So IIR, infinite impulse response filters, are designed by considering all the infinite samples of impulse response. And second question, for direct relationship between analog and digital frequency, the dash should map into unit circle in dash. So IR filters, for designing of IR filters, we should first design analog filter. From analog filter, we have to transform to digital filter. So for doing that, so what we should map? So we have four options. And the answer for this is we should match the imaginary axis in S plane to the unit circle in Z plane. We are transforming the domain from S domain to Z domain. So analog transfer function is H of S and the digital transfer function is capital H of Z. So for converting analog to digital filter, the imaginary axis in S plane should be mapped into unit circle in the Z plane. Third question, in analog to digital transformation, the stability is preserved by mapping dash into the interior of dash. So in the digital filter design, once we are designing a filter, that filter should be of stable. To maintain stable, so what is the mapping we should follow? So we know for analog to digital transformation, we are mapping the S plane with the Z plane. So for that, the mapping is left half of S plane should be mapped into the interior of unit circle in the Z plane. So we have studied for maintaining stability, the poles in the left half of S plane. The poles in the left half of S plane should be mapped into the interior of unit circle in the Z plane. So by doing so, we can justify that our digital transformation, analog to digital transformation, is stable and we have designed a stable filter. Next question, the IAR filters will not have linear phase characteristics. Is it true or false? So IAR filters will not have linear phase. Yes, it is true. So linear phase refers to the condition where the phase response of the filter is a linear function of frequency. So frequency and the phase should be of linear, but when designing IR filters, we should not able to maintain this linearity. So as we are mapping, so that linearity is missing, so that delay or phase distortion will occur in IR filters. So that is one of the drawback. For overcome that, we are using FAR filters. FAR filters will have linear phase. IR filters will not have linear phase. Next, in digital domain, the processing of infinite samples of impulse response is practically not possible. Hence, direct design of IAR filters are not possible. So, we have solved many problems. In IAR, first we should design analog filter and then we should convert to digital filter by means of some transformation technique. So, they are telling here in digital domain, we have to process infinite samples, which is practically not possible. Is it correct or not? Yes, it is true. That's why we are not able to design directly the IR filters. So answer for this is true. So the technique used to approximate the ideal frequency response of analog filters are. So by using which technique we are approximating the ideal frequency response of analog filter. So practical frequency response will deviate with the ideal, but we have to approximate that response to ideal one. For doing so, what are the approximation we have? So four choices are given. So last option, both A and B is correct because Butterworth approximation as well as Chebyshev is widely used. There is no approximation called Taylor approximation. So why these approximations are used? So to approximate the ideal frequency response of analog filters. Next, the technique used to transform analog filter to digital filter or impulse invariant, bilinear transformation, approximation of derivatives, all of the above. So which technique is used to transform analog filter to digital filter? So answer for this is all of the above. We are using impulse invariant method, BLT method as well as approximation of derivative method to transform analog filter to digital filter. Next, for stable analog filter, the poles should lie on dash. So we are going to design analog filter. We should design it as a stable one. For that, poles should lie on where? Or origin of S plane, left half of S plane, right half of S plane or imaginary axis. The answer is left half of S plane. So when the poles are lying on the left half of S plane, we can say that analog filter is stable. Next, for stable digital filter, the poles should lie on the dash. So for analog, it should lie on the left half of S plane. For digital, it should lie interior of the unit circle in Z plane. In the Z plane, we are drawing a unit circle. Inside that unit circle, our poles should lie. Then only we can say that digital filter is stable. Next question, the two properties which are preserved in analog to digital transformation are. So, while we are converting an analog IIR filter to digital IIR filter, what are the two properties it should be preserved? Stability and linearity, linearity and causality, stability and causality, none of the above. So, we know, so that filter should be stable. So, we can have A and C as the choices. The next one is linear or causal. So that filter may be linear or non-linear, system may be linear or non-linear. So the answer is stability and causality. So it should be measurable. So the filter should preserve stability and causality. The tolerances in the pass band and stop band are called what? So we know in the filter we will be having pass band and then stop band. In between that we have transition band. So what is the tolerance in the pass band and stop band? That is called as ripples. Next, for causality of analog and digital IR filter, the number of zeros should be what? It should be greater than number of poles or less than or equal to, equal or greater than number of poles. So for that analog and digital filter to be causal, it should be measurable. So to be causal, the number of should be less than or equal to number of poles. So number of zeros should be less than or equal to number of poles. For realizability, the transfer function of analog filter should be a rational function of S and the coefficients of S should be real. So we have to realize the transfer function of the analog filter. For that rational function of S and coefficient should be real. Is it true or false? Yes, it is true. Next, we are going to see a problem. When such type of problems can be asked in online examination, you can use the virtual calculator present in the examination window. So, in the impulse invariant transformation, the analog system with the filter transfer function h of s equal to 0.3 divided by s plus 0.7 is transformed to a digital system with the transfer function. So, analog filter of transfer function h of s is transformed to a digital filter of transfer function h of z. What is that h of z? They are asking. The method used to convert that analog to digital IR filter is IIM method, impulse invariant transformation. What is the answer for this is? So very simple, you can solve it by directly seeing, no need to put the formula. So the formula is using IIM method 1 by s plus pk equal to. So if the transfer function is of the form 1 divided by or some constant divided by s plus pk, it is nothing but in digital 1 divided by 1 minus e power minus pk t into z power minus 1. So in IIM method, the analog function is sampled to get the digital filter. So that t is nothing but sampling rate here, sampling interval t. So when we see here the pole value is 0.7 but we have only one pole, so P1 is 0.7. Directly we can substitute in the formula. So instead of 1 we have the constant here. Let us keep the constant. H of z equal to 0.3 divided by 1 minus e power 0.7 t into z power minus 1. Directly from by seeing the formula question itself we can directly write. So 1 instead of 1 we should use 0.3. 0.3 divided by 1 minus e power minus 0.7. So the answer is option B. So if you know the formula, what is the formula here in IIM? So it is of the form 1 by s plus pk. The transformation is 1 divided by 1 minus e power minus pk t into z power minus 1. In this problem t is not given, we have to assume t as 1. As t is not given, let us assume this t as 1 millisecond or 1 second. Okay. So answer is h of z equal to 0.3 divided by 1 minus e power minus 0.7 t into z power minus 1. An analog filter has poles at s equal to 0, s equal to minus 2 and s equal to minus 1. So it is having 3 poles. That filter is having 3 poles. If impulse invariant transformation is employed, then the corresponding poles of digital filters are respectively. So in the first sum transfer function is given, in this sum poles are given, poles of analog filter is given and poles of digital filter we should find out. So the same formula we can use here. So if the form 1 plus s plus pk means 1 by 1 minus e power minus pk t is z power minus 1. So poles are given directly. So s plus 0. If the pole is s minus 2, the transfer function is s plus 2. And s plus minus 1 means the transfer function is s plus 1. So when we substitute here, it is nothing but 1 minus e power 0 t z power minus 1, 1 minus e power minus t 2t z power minus 1, 1 minus e power minus t z power minus 1. So the answer is here e power 0t. Here we have to take only the poles. We have transformed here and this is our pole. Let us take this pole alone. Okay. So answer is option B, 0 e power minus 2t e power minus t. The hint here is whatever s is equal to this one, this is our pole value, directly we can substitute. So 0 e power minus 2t, because we have e power transformation, so e power minus 2t e power minus t. So by having the pole value directly we can write. Okay. An analog filter transfer function is h of s equal to 3 divided by s plus 1. When the filter is transformed to digital filter using impulse invariant transformation, what are the poles and zeros of the filter? So they are asking, it is converted to digital. After converting to digital, what are the poles and zeros? Here, for this analog, the pole is minus 1 and the 0 is, there is no 0. So 0 at z equal to 0 and pole at minus 1. For digital, they are asking to find out. So we have to use IIM formula. So h of s nothing but transfer function. In this transfer function, numerator represents zeros and the denominator represents poles. So we know the formula in IIM, it is 1 by s minus pk equal to 1 divided by 1 minus e power minus pk t power z power minus 1. So 3 divided by 1 minus e power minus 1 t, because the pole here is minus 1. So if the s plus pk, so 3 divided by 1 minus e power minus 1 value is 0.368 z power minus 1. So when this z power minus 1 is written as here divided by z, means after solving this we can have the right hand side as 3z divided by z minus 0.368. So here numerator represents zeros, there are no such zeros here, so zeros at z equal to 0. Pole means this should equate to 0. Equal to 0 means we will be getting 0.368 as the answer. So in the digital filter, the numerator represents 0 and the denominator represents the poles, and the pole value is 0.368. So option number A is the correct answer. For this transfer function, the poles and zeros are located at z equal to 0 and pole at z equal to 0.368. And this is very easy question. In impulse invariant transformation, the digital filter frequency omega for a given analog frequency ohm is given by. So analog frequency is ohm and the digital frequency is omega. In IIM, how it is related? So it is related very linear. It is direct relation, linear relation. Analog frequency multiplied by the sampling time gives the digital frequency. So omega equal to ohm into T. So what is the concept of IIM? The analog transfer function is sampled by a sampling interval so that it is converted to digital filter of transfer function h of z and digital frequency omega. So see here omega and ohm are linear, they are maintaining linear relationship. So in IIM, so the frequency relationship is linear here. Next, in dash transformation, the impulse response of digital filter is the sampled version of the impulse response of analog filter. Nothing but impulse invariant. Because analog filter impulse response is sampled so that we are getting the digital filter impulse response. So this is nothing but impulse invariant method. Next, in dash transformation, any strip of width 2 by t in S plane is mapped into the entire Z plane. So what is the transformation? That transformation nothing but impulse invariant transformation. Any strip of width 2 pi by t in S plane is mapped into the entire Z plane. The phenomena of high frequency components acquiring the identity of low frequency components is called ripples, aliasing, sampling, frequency overlapping. So the high frequency component is overlapping with the low frequency component. So that is called as aliasing error. In impulse invariant or bilinear mapping, the dash poles of S plane are mapped into dash of unit circle in Z plane. So this is very important. In IIM method or bilinear, how the poles in S plane are related to the how in the Z plane. That is much more important. In this mapping, the left half poles of the S plane are mapped into the interior of unit circle in Z plane so that we can maintain the stability of the filter. So already we studied for maintaining stability of the filter, left half, the poles in the left half of the S plane should be mapped to the poles present in the interior of the unit circle in Z plane. And next, in impulse invariant mapping, the right half poles of S plane are mapped into dash of unit circle. In the previous question we have discussed, left half poles in the S plane should be mapped inside the interior of the unit circle in Z plane. Now what happens if the poles are in the right half? So if it is in right half, we should map into the exterior of the unit circle. By doing so only we can maintain stability. If the poles are in the right half, we should not map that to the interior of the circle. Okay, it should be mapped only to the exterior of the unit circle. So this is our S plane, means this is our left half. So this should be mapped to the Z plane. In the Z plane, we will be having the unit circle. In this unit circle, it should be inside the, unit circle inside, the pole should lie. Okay. The impulse invariant mapping is dash mapping, whereas bilinear mapping is dash. So very important question. Impulse invariant mapping is many to one because right half is mapped to exterior, left half poles are mapped to interior, and the imaginary axis is plotted inside the origin. Like that we have many to one mapping, whereas bilinear mapping it is one to one mapping alone. In impulse invariant or bilinear mapping, the poles on the imaginary axis in S plane are mapped into the dash in Z plane. It is mapped in the unit circle in the Z plane. Next, in impulse invariant transformation, the problem of aliasing is due to many to one mapping. So many poles in the S plane are mapped to unit circle. So this, by doing so, there will be aliasing problem. Is it true or false? Yes, it is true. So as we are mapping many to one, we are having the aliasing error. In impulse invariant transformation, the relation between analog and digital frequency is non-linear. So relation between analog and digital is non-linear in IIM method. True or false? It is false, because we have studied omega. Digital frequency omega is linearly related to analog frequency by a factor called T, sampling interval. So they are linearly, omega is linearly proportional to ohm. So the given statement is false. In impulse invariant transformation, the analog pole at S equal to minus Pi is mapped into a digital pole at Z equal to e power minus Pi t. So we have solved some example problems. Yes, it is true. So poles in the Z plane are mapped, poles in the S plane are mapped in the Z plane. Next is a problem. Obtain the impulse response of digital filter corresponding to an analog filter with impulse response h of t equal to 0.5 e power minus 2t and with a sampling rate of 1 kilohertz using impulse invariant method. So in transfer function will be given here. The impulse response of the analog filter h of t is given. We should find the impulse response of digital filter. Impulse response of analog filter is h of t. Impulse response of digital filter is h of n. We know what is the concept of impulse response. We should sample the, by sampling the impulse response of analog filter, we can get the impulse response of digital filter. So here is the method. So h of t is given, nothing but analog filter impulse response, and h of n we should find out. So if you are using IIM, we are sampling. So this we are sampling at some n into t time, sampling time. So in the sum f is given, frequency is given. So from that we can find the time interval t equal to 1 by f. So 1 divided by 10 power 3, it is 10 power minus 3 second. So instead of small t, we should substitute this value. So t equal to n into capital T. So capital T is 10 power minus 3. In the h of t, we are replacing this small t into n into capital T. So e power minus 2 into small t, instead of t we are putting n into capital T. So minus 2 into 10 power minus 3, this n is taken as the power here. So if we calculate e power minus 2 into 10 to the power of minus 3, it is 0.998 whole power n. So we have transferred the impulse response of analog filter into impulse response of digital filter. Option C is the correct answer. And I have forget to change the thing also. So C is the correct answer. I have pasted all those things. So answer is 0.5, 0.99 whole power n. So 30th question, IR filters or recursive filters, is it true or false? Yes, it is recursive filters. Recursive filters means those filters will have feedback. So output is fed back to the input. So as the filters are, as the output is fed back to the input, so when we give an input as impulse, the output will be of many impulse responses. It is a recursive filter. So which of the following filters cannot be designed using IIM? So using IIM, which filter we cannot design? It is nothing but high pass filter. So in high pass filter, we will be having aliasing error more compared to other thing. And which of the filter we can design very easily is band pass filters. Using IIM, we can design easily the band pass filters. So thank you for watching my channel. Keep me supporting. I am posting videos related to MCQ of antennas and as well as